Welcome to Understand the Math. In this video, we're going to talk about how to find the domain of a composite function. It's a concept that sounds tricky at first, but once you follow the steps that I'm going to teach you, it's not hard at all. We'll walk through 2 example problems so that you can learn exactly what to do. Let's get started. There are 4 steps that we're going to need to follow to find the domain of a composite function that we're going to call f of g of x. The first step is to determine the domain restrictions of the inner function g of x. The domain of f of g of x excludes any number not in the domain of g of x. The reason for this is that g of x is the input into the function f, and this input, which is our inner function g of x, must be defined in order for f of g of x to be evaluated. We can't evaluate f of g of x for numbers where g of x is not defined. The second step is to find the composite function f of g of x. If you need a review on that, I have a video that walks you through how to find a composite function. The third step is to identify additional domain restrictions from the composite function f of g of x. There may be additional numbers excluded from the domain of f of g of x that were not already excluded from the domain of g of x. Sometimes there are, and sometimes there aren't. I'll do an example of each of these cases. Our last step is to just state the final domain of the composite function. Let's now look at our first example. We're going to find the domain of f of g of x, and we're given f of x and g of x. We'll work through this problem step by step. The first step is to find the domain restrictions of the inner function g of x. Our inner function g of x is equal to 3 over x. When we look at this function, we notice that we have an x in the denominator. We can never have a denominator that's equal to 0, so this means that x cannot be equal to 0. The reason for this is 1 divided by 0 is undefined. Let's highlight this, put it in our pocket, and we'll come back to it. Our second step is to find the composite function f of g of x. Let's write down that f of g of x is equal to f, and what we're going to put inside here is g of x, which is 3 over x. Now we have to figure out what this is. Let's go back up to our f of x. Wherever you see an x, what we're going to do is plug in 3 over x. So this is equal to 3 divided by x up top, and then in the denominator, we have another 3 divided by x plus 2. Now we have to simplify this. Because we have a term in the top and a term in the bottom that's divided by x, the easiest way to simplify this is we're going to multiply the top by x, and we're going to multiply the bottom by x. And the reason that we can do that, it's just like multiplying by 1, because x divided by x is equal to 1. When we simplify the numerator, we get a 3. And when we simplify the denominator, we have 3 divided by x times x, which gives us 3 plus 2 times x. And let's go ahead and highlight this because this is our composite function. Now let's move on to step 3. Step 3 tells us that we have to identify any additional domain restrictions from our composite function. When we look at our composite function, I'll go ahead and circle it. Notice that we have a denominator. Just like we saw for g of x, we cannot have a 0 in the denominator. Our additional restriction is going to be that 3 plus 2x cannot be equal to 0. Let's go ahead and solve for x. This gives us 2x is not equal to minus 3, which gives us x is not equal to minus 3 halves. And we'll highlight that just like we did with g of x. The two expressions that I highlighted in yellow, those are our restrictions for our domain. And we're going to use those here when we go on to step 4, which tells us that we have to state the final domain of our composite function. I think it's usually easiest if we take these two restrictions and we put them on our number line. So I'm first going to say that x is equal to minus 3/2, and then I'm going to say that x is equal to 0. These numbers are excluded, so we're going to draw an open circle at these two numbers. And let's note then that x is valid in this region, in the region between minus 3/2 and 0, and in the region to the right of 0. Let's now state our domain. Our domain is going to look like this. Whenever we have an open circle for a number that's not included, we're going to put a parenthesis. So let's go ahead and let's mark some parentheses like this, and that will help us. Our domain then is going to be from minus infinity to minus 3/2, union, that's marked with a U, minus 3/2 to 0, and then from 0 to infinity. So it just includes all numbers not equal to minus 3/2 or 0. Let's now look at our second example. It's very similar to our first example, but we have different functions. We are going to compute the domain of our composite function f of g of x, but now our f of x is x squared plus 4. It's a polynomial, and our g of x is a function that involves a square root. Let's go ahead and let's walk through our steps. The first step is we determine the domain restrictions of our inner function g of x. Let's write down what g of x is. So our g of x is the square root of x minus 2. We can only take a square root of a positive number, and that includes a number that's equal to 0. So we're going to have to state that x minus 2 has to be greater than or equal to 0. Now we'll solve for x, and we get x is greater than or equal to 2. We'll highlight that in yellow because that is our domain restriction for our inner function. Now let's complete our second step. We're going to find our composite function. Our composite function is f of g of x, and it's equal to f, and what goes inside f is g of x, which is the square root of x minus 2. Let's look back up at f of x, and I'm going to highlight the x. To compute f of the square root of x minus 2, wherever you see an x, we're going to plug in the square root of x minus 2. Let's see what that gives us. This is the square root of x minus 2 squared plus 4. Now we have to simplify this. If we take the square root of an algebraic expression and then we square it, those two operations cancel each other out, and we just have x minus 2 plus 4. And this gives us a value of x plus 2. I'm going to highlight this because this is our composite function. Our third step is we're going to look at our composite function and see if there are any domain restrictions. Our composite function is f of g of x is equal to x plus 2. Let's notice that this is a polynomial, and all polynomials have no restrictions on their domain. They are defined for all real numbers. So for the restrictions, let's just write down none. And I'll go ahead and highlight that. Let's pull this back down so we can see our first restriction. Our last step then is to just state the final domain. We have a restriction from g of x, and that says that x has to be greater than or equal to 2. So on our number line, we're going to put the number 2. And in step 3, we found that we have no restrictions to our composite function that aren't from g of x, so we don't have to add anything else. Let's notice that at 2, that number is included, so we're going to draw a closed circle. And let's indicate then that it's valid for all numbers to the right of 2. To write this mathematically, we're going to put a square bracket here. See if we can squish that in, because 2 is included. We can then write that our domain is the following. It's going to be all numbers, square bracket, 2 to infinity. And there you have it. Finding the domain of a composite function involves considering restrictions on both the inner and the resulting composite function. Don't forget those crucial steps. Analyze the inner function, build the composite function, check for new restrictions, and then state your final domain.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.